Okay, so let's start this one up. If you're still in your train of thought, keep it going. So we have our car moving at 20 meters per second. It's going to encounter some friction. We're no longer hitting the gas. We're just going to let it coast, slow down. So first of all, let's just do the review problem. How are we going to find friction? What's the equation? Mu times Fn, right? And since we're on a nice flat surface, what's the Fn going to be? Same as the weight, right? So mu times mg should give us our force of friction. So mu here was 0.8, 500 times 9.8. All right, what's force of friction? Okay, so that's our force of friction, right? All right, so let's go ahead and do the next one. We're going to find what's our velocity after 10 meters. So again, we're going to use this using the concept of energy here. So we know that work is going to be equal to the change in our kinetic energy. Okay, so we want to figure out, all right, how much work did we do? Well, how would we find work? Force times distance. So we're going to figure out the amount of work that we did. That should equal the kinetic energy final minus the kinetic energy initial. Well, to find out how much work we did, 3920, right, times 10 meters. Now it is important to understand that our force up here is to the left, right? And our distance is to the right. So what kind of work do we have here? A negative work. So you do have to make sure that you have a negative work. And what that means conceptually is energy is being removed. Energy is being removed here. So we had a certain amount of energy. In fact, how much energy did we have? From the previous problem we already know, right? How much was it? 100,000 joules. So we had 100,000 joules, okay, and then we removed 39,000, or almost 40,000 joules. So we have 100,000 minus the 39,200, right? That should be our final kinetic. So conceptually what's going on is our car had 100,000. We took away, through friction, we took away 39,200. Now where did that go? Did we just destroy that energy? Has that energy been destroyed? It's been transferred. Now what kind of energy is it? Is it the energy of friction? Okay, yeah, it got turned into heat energy. So specifically it got turned into heat energy. And conceptually, if you want to understand why it's heat, think of this book. Is this book's going across the table? Right? It's rubbing, it's interacting with the atoms on the table. So as it passes by the atoms, it's kind of moving the atoms with it a little bit. What's going to happen to the speed of the atoms on the table? They're going to speed up. And back in chemistry, what did you learn about atoms moving faster? What does that mean? They have more energy, and we call that heat energy or thermal energy. Right? If you rub your hands together, you're rubbing the atoms, you're making the atoms go faster and faster in your hands, and you can feel that as a thermal type energy, right? Yeah?
Is heat a radiant energy?
Well, heat specifically would be just atoms moving faster. Now, as those atoms move faster, they bump into each other, they cause electrons to jump into higher energy levels. When they fall back down, they release radiant energy, but we're not going to get into all of that. For our purposes, yeah, they're just going to be moving faster, right? All right, anyways, how much energy are we left with? Okay, 60,800 joules. So conceptually, so try to get these concepts. If you're getting the concepts, this whole unit's going to be easy for you. All right? We started with 100. We took away 39. That turned into heat. But we took away 39. We're left with 60. So anyways, I actually asked you for the speed, right? So how do we find the speed? 1/2 mv squared. Yeah, so we'll go 1/2. The mass was 500. And our v is, or looking for a v. Okay, and hopefully our v is less than 20. If it's less than 20, at least we have a decent idea we're doing the right thing. What are we getting? 15.59. So basically 16. Okay. So we're slowing down, right? All right, so let's do the next one, last one. How far until it stops? So G. Okay, can I cover this up? So we want to know how far until it stops. Again, so conceptually, let's think about this. I'll write the equation, but conceptually, think about it. So if our car has 100,000 joules, right? It's moving along at has 100,000 joules, and then it stops. Well, where did all that energy go? Into heat. Specifically, how much work was needed to stop it? 100,000 joules. Right. If you start with 100,000, if you want to stop it, meaning you took away all of its kinetic energy, you had to do 100 joules of work. And so you'll see that as we do the equation, work equals KE final minus KE initial. Well, if our car stops, what's our KE final? 0, right? So you're simply left with work equals negative KE initial. And that's what we just said. If you have 100,000 joules to start with, and the object stops, you had to do 100,000 joules of work on the car to get it to stop. That's a big concept. Like, that's one of those easy conceptual questions that they give you that you should be able to get right. Okay, it's just, you start with 100,000, you stop it, you had to do 100,000 joules of work. Okay, and so this one, they actually didn't ask you for the work. What did they ask you for? How far until it stops. So you'll just go force times distance equals negative 100,000. The force we calculated earlier, that was what? 3920. And again, since it's opposite, you do want to make sure that that's, you can think of it as like a negative force. 3920 times D equals negative 100,000. So how far did it travel? 25.5. Okay. Wait, don't pack up yet. We still got one more problem to do. We got 2 minutes to do it. Okay, what if we doubled the speed? If the speed was doubled. In other words, instead of starting at 20 meters per second, we're going 40 meters per second. Now this one you could also do conceptually. Okay? You could do it mathematically. You could plug in the 40 and go blah 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 and find out what it is. But let's just think about it conceptually. So again, we're going to stop, right? So we're going to be left with the same thing we got over here, where work equals negative KE initial. Okay? So again, you could plug in the numbers here, but let's do it conceptually. If we doubled the velocity, what should happen to the kinetic energy? It should be 2 squared times as large, right? So it should quadruple. So we don't even have to do the math. I know how much it is, right? It was 100,000. I just quadrupled it, so how much is it? 400,000, okay? Or if you just think of it as 4 times as much. Well, that should be equal to our work, which is force times the distance. We didn't change the force. So if we just quadrupled the amount of energy, we have to quadruple the amount to stop, which means what's the distance going to be? 4 times as far, right? So D would have to equal 4 times whatever our D was before. So about 100, 102. Okay, so again, notice like when you're driving, if you double your speed, it would take you 4 times the distance to brake. It takes 4 times as long for you to brake just by doubling the speed.